Thank you. So I'm very pleased to be here today to be able to talk to you about some of the work that we've been doing on binary code decompilation. And in our paper, we focus on improving the readability of the decompiled code in order to facilitate the analysis of malware and manual reverse engineering of binary code in general. So this is joint work with Sergei Deschamps, Elma Gerhards-Badia, and Matthew Smith. And we're from the University of Bonn and Fraunhofer FKE Institute in Germany. So I'd like to start by asking a question. So if I give you a program and ask you to tell me what this program actually does, would you rather have a look at this version of the code, which is the low-level assembly code, or would you rather have a look at this version of the program, which is the high-level source code? And I guess that most of you would rather analyze the source code because it's easier to analyze. And the reason for that is source code has abstractions that help us analyze, that help us to understand the code. These abstractions include things like functions, variables, and control flow structure. However, the version of the source code shown in this example is not very readable and can be rewritten in a much more readable way where you have more meaningful variable names and similar control flow structure. So in general, analyzing well-readable, high-level source code tend to be much easier than analyzing binary code. However, in security, we often only have access to the binary version of a program. And the problem is, when the source code is compiled, all these abstractions are lost, and they are removed from the final version of the program that we have access to. So here where decompilation comes in, so decompilers try to reverse the process of compilation by recovering these abstractions from the binary code, and in order to reconstruct a high-level representation of the program that we can analyze more easily. So decompilers have been studied for over 60 years, and although while a lot of work has been done on improving the quality of decompilers, state-of-the-art decompilers still produce code that is difficult to analyze. And sometimes the decompiled code is so difficult that malware analysts decide to stop reading the decompiled code and go back to analyzing the assembly code directly. Moreover, previous work on decompilation has never included user studies to actually evaluate the usefulness of decompilers for malware analysis. Instead, they rely on some readability metrics, like the compression ratio by comparing the number of lines of code of the decompiled output to the input assembly program, or counting the number of auto statements in the code. While these metrics provide some insights into the readability of the decompiled code, we believe that the usefulness of decompilers for malware analysis need to be evaluated with user studies that involve real malware code. So this is what we did. So at NDSS last year, we presented a decompiler called Dream, where we proposed an approach to produce fully structured code without goto statements. And in this work, starts from this point, and it's about how do we take the decompiled code and put it in a readable form that is easily understandable by human analysts. And for this, we implemented several usability extensions on top of a Dream, and we called the extended version Dream++. And to evaluate our approach, we conducted the first user study on the quality of decompilers for malware analysis. So the first step into designing our usability extensions was to identify the key readability problems in decompiler-generated code. And for this, we talked to several malware analysts to identify the main issues, readability issues they have when analyzing decompiled code, And we also analyzed the decompiled code generated by Dream and by these industry standard hex phrase. And I will give a very short overview about the readability problems we found and we solved. So we grouped the readability problems into 3 categories. Well, first, decompiled code often contains overly complex expressions. And such expressions are almost never found in the source code written by humans, which makes them difficult to understand. This includes a lot of redundant variables, and for this we implemented a technique to recognize shots variables and replace them with a single variable that without changing the semantics of the code. We also found that we have overly complex logic expressions, and to solve this, we used a theorem prover to simplify these conditions. And the third problem is you have a lot of pointer arithmetic that's involved in pointer dereference, and here we implemented several techniques to transform these expressions into a more readable way, which as array accesses. The second problem was the convoluted control flow. So in general, the readability of a program depends on the simplicity of its control structure. And we found several problems related to that in the decompiled code. For example, you have duplicate or inline code. And to solve this, we created a query, an engine for query and to query a code and apply some transformations. So an analyst can simply write a pattern for an inline function that would be, so when this pattern is found, the whole code block will be replaced by a simple function call. We also found some complex loop structures that result from compiler optimizations, and we reversed that. The third category of problems was that decompiled code often lack high-level semantics, and these semantics, such as variable names, this information is simply lost during compilation, and we developed several techniques to give sort of representative names to the variables based on the context in which they are used. And the same, we did the same for named constants. So we have some library functions where some contexts have a special meaning, and the source code they have a textual representation revealing their code, their purpose. But when the code is compiled, you only have basically the value. And as an analyst, you have to look this value up. What this means when you analyze the decompiled code. So we also handled named constants. And so to give you a feeling or an example about these problems, here's an example which shows the decompiled code for the domain generation algorithm for the SIMDA malware as generated by the hex-trace decompiler, which is the industry standard that's used by most malware analysts. And here you see that you have a lot of variables in the code, you have complex expressions, and you have complex expressions with pointer arithmetic. And so the automatic transformation we built in the paper produce a much more simpler code. And here you can easily see that you have like 2 arrays of characters, and you have a simple loop that chooses between these 2 arrays depending on the variety of the loop counter. So in order to evaluate our approach, we conducted a user study. And for this study, we took 3 decompilers. We took our usability, our improved decompiler with all the readability improvement. We took the original Dream decompiler, and we took the Hexphrase decompiler as an industry standard. And we had our participants complete 6 malware reverse engineering tasks. So each task involved the analysis or the reverse engineering of a given function from a malware sample. And to ensure that we have unbiased results, we had to do a lot of kind of juggling with the task order. So we counterbalanced the decompiled orders so that each decompiler will be used in the same frequency at all positions in the study. We also counterbalanced task order so that, for example, some participants, half of the participants start with easy tasks, and then they had the difficult tasks. The other half had it in the other way. And to measure user perceptions, after each task, we asked students few questions, the participants few questions regarding the usability or the readability of the code. And at the end, we showed them the decompiled output generated by all decompilers. And I told them to ask them to give a rating for each of the 3 decompilers. And at all stages in the studies, we didn't tell participants for any of the tasks which compiler is used to generate this code in order to have an unbiased results. And so regarding task selections, we approached 3 independent malware analysts who were not involved in the study or on the work on the decompiler. We told them that we want to conduct a study on malware analysis, and we asked them to provide with malware code snippets that they had to analyze during their work. And we got 6 tasks from involving 5 malware families. We had 2 groups of participants. We invited 36 students who successfully completed our malware bootcamp, which is a lab course where students are introduced to the basic concepts of malware manual analysis and reverse engineering. And we also contacted 31 professional malware analysts. 21 students completed the study, and also 9 professional malware analysts completed our study. So here is the table shows us the results. So here the table shows the average scores achieved during the study. So the columns shows the 2 groups of participants, and so for each cell, you see the average score achieved by each group for each decompiler. And you see here in both groups, you have participant performed better using Dream++ than with Dream, and better than Hexphrase. And unsurprisingly, in all of the tests, the experts were better than the students. But it's interesting to notice that the difference between the scores achieved by students and experts with Dream++ were much smaller than with Hexphrase, showing that the decompiler actually helped the students to solve the tasks. And we also, it's interesting to notice that the average score achieved by the students with Dream++ was better than the score of the experts with Hexphrase. So in order to get a better feeling of the results, so we set a threshold of 70%, and we considered each task to be solved if the score is equal or higher than 70%. And with this, we see that the students solved 3 times as many tasks with Dream++ as with Hexphrase, as also for the experts, they solved 1.5 as many tasks with Dream++ as with Hexphrase. And regarding user perceptions, so we asked questions regarding the 8 questions after each task regarding the usability, like how easy or difficult the readability, how easy it was to read the code, and two questions regarding if the participant trusted that the decompiled code is correct, and to counterbalance, to minimize the response bias, we counterbalance positive and negative questions. And so here's an aggregate shows the aggregate results. So you see in the green for both types of questions and for both groups the positive answer we got. And so here you see a similar trend in all groups where Dream++ achieved the best result, followed by Dream and followed by Hexphrase. And here some comments that we got during the study. So this code mostly looks like a straightforward C translation of machine code. So besides a general sense about what's going on, I'd rather see the assembly. However, with our usability improved decompiler, we heard things like, this code looks like it was written by a human, even if many of the variable names are quite generic, but just the named index variable make the code much easier to read. And so finally, the participants were shown for all of the tasks the code generated by all decompilers, and we asked them to give a score from 1 to 10. And here's the results. So there's a clear trend in the student group. So you see these students liked Hexphrase the least, Dream a bit more, and liked Dream++ the most. While in the experts group, they were a little bit more diverse when it comes to Dream versus Hexphrase, but they give really good score to Dream++. So to sum up, we implemented several usability extensions to improve the readability of the decompiled code generated by Dream. We conducted the first malware analysis user study, and the results show that a human-centric approach to decompilation can significantly improve their effectiveness. And as future work, we're currently exploring other use cases than malware analysis, and we try to combine decompilations with source-based technique to find vulnerability in the code to try to find vulnerabilities in the binary code. So with this, I thank you for your attention and I'm ready to take questions.
Okay, questions? All right, we have a lot of questions.
Debbie Perulli from Marquette University, very interesting work. I was just wondering if Dream or Dream++ has any way to deal with code obfuscation techniques, especially virtualization techniques.
No, we don't really deal with that. So it's normal as a malware analyst, if you have an obfuscated or unbacked code, first to unback the code or to de-obfuscate it, and then decompile it. So we assume that there's a first step where you decompile the code. But even without obfuscations, so you still have not very readable code with Hexphrase, for example.
Okay.
Steli Sadiroglu from MIT. Thanks for your talk. Most sound decompilers use over-approximate analysis, and the over-approximate analysis needs to imprecision. How do you incorporate imprecision in your sort of recomposition of the code?
I'm not sure I got your question correct.
So in order to soundly decompile a piece of code, right, you typically have to do an analysis, and your analysis, in order to be sound, sometimes needs to make a guess, right, about what the code is like. So it leads to imprecision. You might sort of have more sort of targets in the decompiled program than you would normally. So if you're trying to make the code look more readable, how do you take imprecision into account?
Well, all of the optimization that we build are semantics preserving, so they don't change the semantics of the code.
So you're assuming that your decompilation is fully precise and sound?
No, we assume that, so the readability improvement that we implemented in this paper, they are semantically, they don't change the semantic of the code, so we make sure of that.
I think you may be missing a point, but maybe we'll take it offline. Yeah.
Okay. All right, Tim.
Thank you so much. I think this is really interesting. I'm really excited people are working in decompilation. I had sort of two questions. One is, you could imagine that if you applied this Dream++ set of algorithms to code written by a sort of bad monkey programmer, that it might, make it much more readable. Have you tried that sort of thing?
No, we just,
Like I can give you some of my code, for instance.
yeah, would be interesting. But we haven't, so what we took, we just asked the analysts, malware analysts, to provide us with some tasks they had to analyze. So you always can come up with some code or some special cases where the compiler will screw up. But so we followed the approach that we asked them, give us some code where you had to analyze, and we can show how we perform on
I'm
that.
mainly curious if it would sort of clean up bad code from somebody, like me, for instance. But that I can ask you offline. The other question I have is this going to be made open source? Because Hexrays is terrible, and I would love to use something else.
Yes, yes.
Yeah, so we're trying our best to make it available as soon as possible. So we want to make it available so that, at least now for the researchers, but when you write something for research, it's a different story when you want to.
We're happy to help.
Yeah.
Okay. Thank you.
Right. Very good. Okay, two more questions. Jaeyoung?
Okay, Jaeyoung Jung, Microsoft Research. A great work. I'm really happy to see kind of user study paper here at Oakland. So the two kind of questions and comment. So I've spoken to a lot of sort of folks developing tools for code obfuscation, and they seem to have kind of backup tricks to make the code to be less readable. So well, you mentioned that you gathered kind of requirements for usability by talking to developers.
Yes.
But have you looked at some of those like known obfuscation techniques to see what are the kind of the common techniques that they use to make the thing unreadable?
So as I told you, we assume that if a code is obfuscated, that you first run it through an deobfuscator first, and then you give it to us. We found in some of the examples that we tested, there's an example where there was a check to the version of the operating system, and so there was an error in the malware itself. So, which when we simplify the conditions, so using theorem prover, it removed this condition. Well, I mean, you can always write code that you cannot, or that where you have problems, but we haven't tested, we haven't examined like that.
Okay. Thank you.
Okay, we have two more questions. Yes.
Hey, hello. This is Fish from UC Santa Barbara. This is a piece of amazing work. I was there when you were presenting NDS, when you were presenting at NDSS about Dream, and we had a dinner together, if you still remember.
Yep.
I was about to ask like when you were going to open source, or when you're going to at least give us people from academia a chance to use the awesome Dream++, but it has been asked before. So I'm asking, like, can we have a lunch together today as well?
Okay, yes. That's a very good conclusion.
Hi. So I spent a lot of time in Hexrays this past weekend, and so I'm kind of newly reminded of its flaws. One of the things that I find that's really helpful about Hexrays is that you can kind of, as a user, you can slowly give it sort of tips that you've found out. Like you can create structures, you can give things names, and once you start fixing up the types, it becomes a lot better at producing something that looks much closer to C code. Have you guys looked into that at all? Like, or have you just been like sticking? During the study, were you just like sticking code up on the screen for people to use, or
no? We had
did they have the opportunity to interact?
Well, we did the study online, so we had an online study platforms because we wanted to invite malware analysts so that they can participate remotely. And for that, we had a sort of an integrated text editor where you can change the code, like rename some variables and add some comments and so on. So you would get a fully integrated text editor where you can change the code or improve the code as you analyze it. So we tried our best to be as similar to Hexrays as we can.
Okay, thanks. I just want to say this is really cool work, and I'm really excited about it.
All right.
All right.